We defined the term of linear combinations of vectors in a previous video. That is certainly an important concept when it comes to sets of vectors. Another important concept is the idea of the span of a set of vectors, which is what we're going to look at in this video. To begin, matrix multiplication allows us to rewrite a linear system in the form ax equals b. We saw that in some previous videos. Besides being a more compact way of expressing a linear system, this form allows us to think about linear systems geometrically, since matrix multiplication is defined in terms of linear combinations of vectors. And specifically, when thinking about vectors in R2 or R3, this idea of a linear combination certainly has the geometric interpretation that we've already explored. So we're going to be kind of thinking about linear systems geometrically via this idea of linear combinations, and then also kind of thinking about solutions of linear systems geometrically. We're going to look back now at two fundamental questions we had when it came to linear systems. One was this idea of existence, or this question of existence. Does the equation ax equals b have a solution? And then uniqueness. If there is a solution, is it unique? So let's look at an example. Consider a 3 by 3 matrix A, 1, 2, 0, 0, 1, 1, 1, 3, 1, and a vector B, 3, 0, 3. So is the equation AX equals B consistent? If so, find a solution. So remember, sort of the way we can approach this is by setting up a system of equations to solve for this vector X if it exists. And then ultimately we discovered, that the augmented matrix for that system would have A as its coefficient matrix and B as kind of the right-hand side of that matrix. So let's set that up here. So there's our coefficient matrix A. We'll put our vertical line, and then we'll put that vector B. And now we can row reduce this. I'm going to go through and actually go through the steps of row reducing this by hand. If you are sort of at this stage kind of pretty comfortable with the row reduction algorithm, then you're welcome to use some technology, Sage or your calculator or Python or the online linear algebra toolkit, some of those tools that we had explored earlier. But I do think it's a good idea to just kind of every once in a while go through that algorithm again by hand. So first we'll do this R3 minus R1. So our first two rows will remain unchanged, 0, 1, 1, 0. And then our third row becomes 1 minus 1 is 0, 3 minus 2 is 1, 1 minus 0 is 1, 3 minus 3 is 0. And then we can do R1 minus 2R2 and R3 minus R2. So we get 1, 0, negative 2, 3, 0, 1, 1, 0, 0, 0, 0, 0. So we do see that this particular system is consistent. We notice that we're in reducer echelon form. We do not have a pivot in our final column there. We also do not have a pivot in the third column. So if x is the vector x1, x2, x3, then we would say that x3 is our free variable. That column has no pivot, and we can write x1 and x2 in terms of that. So let's just go through that whole thing, just because it's again sort of good practice. So we'd have x. Actually, let's do it like this. So let's write out our solutions for each one. We have x1 would equal 3 plus 2x3. We'd have x2 would equal just negative x3, and then x3 is x3. So if we wanted to write this whole solution out in that kind of parametric form, we'd get the vector 3, 0, 0 plus scalar multiples of the vector 2, negative 1, 1. So this is all related to this idea of the span of a set of vectors. So let's go ahead and define that, and then we'll kind of go back and consider that relationship. So we say that the span of the vectors v1, v2 through vn is the set of all linear combinations that can be formed from those vectors. Namely, if A is the matrix whose columns are given by those vectors, v1, v2 through vn, then the span of the vectors consists of all vectors B for which the equation ax equals b is consistent. And so, all of this kind of aligns with how we've defined matrix multiplication and linear combinations. Kind of the only thing that is sort of new here is the introduction of this term span. Although we will sort of see that this idea of spanning is going to play a pretty big role in a lot of what we do later on. But for now, it's really just sort of defining some new terminology. Let's do an example here. Consider the matrix A is 1, 0, 1, 0, 1, 1, 1, 1, 2. Determine whether B1 equals 2, 3, 5 is in the span of the columns of A. And so we might, have also worded this as sort of like, consider the vectors B1 equals 1, 0, 1, V2 equals, just writing out the columns of A as sort of vectors, 0, 1, 1, V3 equals 1, 1, 2. And then we could have kind of asked equivalently, is B1 in the span of these vectors? So sort of two ways of asking that question, one relating to kind of the columns of a matrix, the other kind of going back to just a set of vectors. Either way, we're looking to see, is there a solution to the equation ax equals b1? So we can set up our matrix, our augmented matrix for that system. Again, putting A as our coefficient matrix and B1 as the kind of right-hand side. And I am going to this time just kind of rely on some technology. So I will take a second here and plug this into my calculator and row reduce this. And you're certainly welcome to try this by hand or also be row reducing on a calculator. So we go through that row reduction. Okay, and the result here is 1, 0, 2, 0, 1, 1, 3, and then 0, 0, 0, 0. Okay, and so what we see is no pivot in the last column. So yes, B1 is in the span of those vectors. And furthermore, we could identify the actual linear combination or an actual linear combination, I should say. So again, if our weights are given by x1, x2, x3, we actually see we have infinitely many solutions here. So we have free variable x3, and we'd have x1 equals 2 minus x3, x2 equals 3 minus x3, and x3 is a free variable. So suppose, for example, suppose we decide that we want x3 to be 1, then that would tell us that x1 would be 2 minus 1, which would be 1, and x2 would be 3 minus 1, which would be 2. And so what we can show is that, let me come up over here to show this, that B1 should equal x1, which is 1. So 1 times the first column of A, plus x2, which we found to be 2, times the second column, 0, 1, 1, plus 1 times the third column, what we chose for x3. And this is all sort of extra work that we don't have to do for this question. If all we are being asked is this vector in the span of these other vectors, then the row reduction showing that the system is consistent is plenty. But for our first example, or one of our first examples here, might as well sort of go through and kind of see how this is all related. And if you go through and do all this math, you would see that B1, let's just like quickly do that calculation. 1 plus 0 plus 1. So yes, we do get 2. 0 plus 2 plus 1, we get 3. 1 plus 2 plus 2 is 5. So that does, in fact, work. And we can see not only is B1 in the span of these vectors, but there are sort of infinitely many linear combinations of those vectors that would get us to B1, since we did have a free variable. Let's do another example where we have the same matrix, but a different vector, B2. You might have suspected we were going to have a B2 since we were talking about B1 before. And so if we set this up in the same way, 1, 0, 1, 0, 1, 1, 0, 1, 1, 2, 3. Again, I'm going to use sort of technology to take care of that row reduction for us. And if you feel like you would like more practice doing the row reduction by hand, you can do that. Or if you want to practice using Sage or a calculator, definitely go ahead and do that. So if we row reduce, the result here is 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1. And so we have a pivot in the last column. And so that last row now reads 0 equals 1, which again is not true. So this tells us that there are no solutions. And so we have the fact that no, this particular vector is not in. So no solutions. Therefore, B2 is not in the span of these vectors. Okay, so that's sort of like the definition of spanning and kind of algebraically how we can check for it. What we're going to see in a future video is kind of the geometry of spanning and what some of the other roles of sort of looking at the span of a set of vectors would be, and kind of apply it to a variety of problems.